state spaces will be, none of them contain critical points. Okay? I'm not assuming F is compact, F is Morse. In special case where we apply this, we are going to assume typically F is compact and F is Morse. In which case, this is forced to be compact. Because it's a closed set, inverse of closed set is closed and closed set. But I'm not assuming that. All I need is this to be compact. M could be a non-compact. Then A. So this diffeomorphic to NP. In fact, you can say more. You see that clearly there is an inclusion of MA into MB, right? Because what is MA? It's all the inverse images up to A. MB is all the inverse images up to B. So MB contains way more stuff than it, and the inclusion is a deformation ring track. You can think of it this way. In fact, one can show that the inclusion of MA no deformation ring track fine if you don't go. Okay, so the point is that these two accumulated level sets are different. In this picture, of course, this is a good term of my A. I could choose this as my B. In which case I get this. And it's pretty clear in this example at least that these two are different. Because they're both different. But of course, you want a controlled diffeomorphism. So the proof usually goes by looking at the vector field, the minus gradient of F. And so technically, to find a gradient, you need a metric. And one metric, I'm not say anything more because I don't want to go into the proof. But you use the flow lines, and then you have to sufficiently normalize the vector field and the flow lines obtained by looking at the gradient of F. And then you can essentially flow from here to here and then you push to here down. Yes. No, so I'm saying this will sort of follow from the proof that this is a so that diffeomorphism will be that there's a one parameter tangent map from MB cross I to MB, which is MB at 0 and at time 1 it maps to M. So you cannot, I'm not saying you literally push everything down. I mean, these things also have to be pushed down sufficiently because it's a diffeomorphic. The claim is that they're diffeomorphic. This is a weaker word. Right? But this will be useful if you want to control the positive. Yeah, so this inclusion is a smooth inclusion of submanifold, and the map from here to here is a smooth. Yeah, it's everything is a smooth setting, but I'm mentioning this because this is the one which is used immediately when you try to attach cells and so on. But this thing is a smooth map, so that's why you need compactness because you want to extend the vector field appropriately outside by 0 and so on. Otherwise, you should not have global extension. Oh, so deformation ring track, as I said, is just so if you have two spaces, A inside X, deformation ring track to A means there should be a map from X to A. So that when you go from A to X by inclusion and you come back, it's identity of A. But you can start from X, go to A, and then come back by inclusion to X. That's not going to be identity, but that's homomorphic to the identity. So if you take a closed disk, that deformation ring tracks to the origin. So that's the radius. So if you are used to homomorphic equivalences, this is saying that these two are homomorphic equivalent, but that's obvious if they're diffeomorphic. Yeah, so you don't want to put too much attention to this diffeomorphic. Okay, this is one, and this is again for the same setup. let f of t equal to c. Just whatever the values it takes. Given point of x having index, which means in the local coordinate it looks like this. So again, you will be applying this to a Morse function. So this is then obviously true by. So then, if so the thing is, you look at f inverse c and you look at a slightly thickened version of f inverse c, which means you look at f inverse c minus epsilon and c plus epsilon for epsilon something this form. So f inverse c of course contains p, which is the critical point. So in our example here, this was what we had, right? This would have been your c. That's your p. So now we are saying, suppose there is sufficiently small epsilon, so that this contains no critical points other than p, because p is already in there. If I take a little bit of thickening here, what do I get? In this particular case, I have exactly one critical point, and thickening is going to look like however it is. That sort of has gone through the critical point, so it has opened up. So this will be your c minus epsilon and c. Yeah, so if it only has one critical point, which is p and nothing else, if over if then m c plus c plus epsilon is m subscript c is just this. So let me say what this means. So if you are not used to what the type means, this
You will get it where c minus epsilon c plus is that to compact, no?
yes, I guess yeah, that's true. It is to compact. I think that will be here. Yes. Yeah, it's the same. Yeah, mean the equation which you and it's compact and it contains no critical points. Then this has the same homotopy type as this. So essentially what this means is you look at this thing, which would be, let's say this amount, okay? And then you are attaching to that, which means you literally take, so lambda cell is nothing but closed lambda disk. Yes, so I look at a closed disk of dimension lambda. So that's a user terminology to call it a lambda cell. So a 2 cell is a closed unit to this. You are attaching this disk by some specific map to this space. So you get a space which is not a manifold, but it turns out that this particular manifold with boundary will be homotopy. There should be a map from this union, this lambda disk, to this, and that map is a homotopy. So I'm not claiming that they are diffeomorphic, because if you take a manifold and you attach a one cell, which is like a string, you are attaching that last time, right? Remember going from here to here. This is not a manifold. This cannot be actually with homotopy. But this was homotopy equivalent to this, because you can perform this by first thickening this, making it into a strip, and then you can start taking more and more and getting something. So that's essentially what is saying. So you have to know how to attach, but the cell you are attaching is this lambda, which is the index of. Okay, so let me draw the example of the torus to see where we are applying all these things. Now, we have already seen this, but yes, sir. So what? No, the attaching map comes from these coordinates. The lambda cell that you get will come from these coordinates. So you have to look at what this looks like in an Rn coordinate. So if you look at x squared minus y squared, you know what the level sets are like that. So the T lambda will come from this less than or equal to 1, and you set these to be 0. So that would be the lambda sub that in that local coordinate system. If it comes from that, it's not that you just attach it randomly. So I cannot just attach something like that. That obviously is not. So we have to look at T in this coordinate system